In this segment, we'll discuss contraction mappings, which are important in the theory of dynamic programming, so you'll be seeing a lot of this material in various courses. Here's the plan. We'll begin by defining contractions and pseudo-contractions, and then we'll state and prove our main result, which is the Banach fixed point theorem. And this states that a contraction in any complete metric space has a unique fixed point, and also gives us a procedure for computing this fixed point to a high degree of approximation. And we'll end by observing that this result does not apply to pseudo-contractions unless the metric space is not just complete but also compact. But we'll deal with the proof of that claim later in the course. So here's the definition. Suppose that xd is a metric space, so x is a set and d is a distance function. We say that a function t, which maps x to itself, is a pseudo-contraction if for any 2 points xy in the set x, the distance between these 2 points is strictly greater than the distance between their images. And a contraction if there exists a real number lambda strictly between 0 and 1, such that the distance between the images of x and y is less than or equal to lambda times the distance between the points. Now clearly a contraction requires a more restrictive condition to be satisfied, and so every contraction is a pseudo-contraction. Now usually when using these ideas, x is going to be a set of functions and d will be the sup metric. So just keep this example in mind as we proceed. Now in general there will be many values of lambda for which the inequality on the slide holds, and the infimum of the set of all such lambda is the contraction coefficient. Just recall that the existence of this infimum follows from the completeness of the real numbers. Now since T is a self-map, it maps a set onto itself, we can iterate this map, so we can let T squared of x be the image of x and so on, and T to the n of x is the nth composition of T with itself. We say that an element x star of x is a fixed point of T if T maps that point onto itself, and it's clear from the definitions that pseudo-contractions and also contractions have at most one fixed point. So to see this, let's just go back to the definition, which you see here, and you can see immediately that if there were two fixed points x and y, since T of x equals x and T of y equals y, this inequality cannot possibly hold. Now here's the main result we want to prove. Suppose that x is a complete metric space, and the self-map T is a contraction. Then there exists a unique fixed point in x, and furthermore, starting from any point in the metric space, if we iterate this map, the limit of the sequence of points we get is precisely the fixed point x star. So let's go through the proof of this claim. Consider any point x0 that is not a fixed point of x, and we'll define the sequence xn by simply iterating this map. So xn is the image of xn minus 1 for all natural numbers n. And we're going to show that this sequence xn is Cauchy, and therefore from the completeness of x is convergent. So first note that since every term in this sequence is the image of its predecessor, the distance between xn plus 1 and xn is just the distance between the images of xn and xn minus 1. And by the definition of a contraction, there must exist some lambda less than 1, such that this distance is less than or equal to lambda times the distance between xn and xn minus 1. Now we can apply the same reasoning to the distance between xn and xn minus 1. This itself has to be less than or equal to lambda times the distance between xn minus 1 and xn minus 2. And so on, reasoning in this way, we get the expression on the slide, which is that the distance between xn plus 1 and xn must be less than or equal to lambda to the n times the distance between the first two terms in this sequence. Now to show that this sequence is Cauchy, let's consider any natural number L and any k that is larger than L plus 1. Now from the triangle inequality, the distance between the terms xk and xl has to be less than or equal to the distance between xk and xk minus 1 and the distance between xk minus 1 and xl. Now we can apply the triangle inequality to the second term in this expression to get the following, and we can repeat this process until we end up on the right side of this expression with a sum of distances where each distance involves adjacent elements in the sequence. Now we're going to use the inequality that we obtained earlier, so let's remind ourselves of that. You see it here, the distance between adjacent terms, xn plus 1 and xn, is less than or equal to lambda to the n times the distance between the first two terms in the sequence. Now if we plug that into the expression on the right, we obtain the following, which expresses the distance between xk and xl in terms of the distance between x1 and x0 and the sum of various powers of lambda. Now we just rearrange this expression. We take lambda L out of the parenthesis and reverse the order of the terms in the sequence, and then we'll just add a few more terms into the sequence so that we end up with an infinite sequence, and since we're adding strictly positive terms, we get a strict inequality in the expression. Now we just use the formula for the sum of a geometric series, is lambda to the L over 1 minus lambda times the distance between the first 2 points in this series. Now this expression of course goes to 0 as L goes to infinity. And so therefore for all k bigger than L plus 1, the limit as L goes to infinity of the distance between xk and xl is 0. Now you should go back to the definition of a Cauchy sequence and convince yourself that this implies that the sequence xn is in fact Cauchy. Now since the sequence xn is Cauchy and the metric space X is complete, this sequence must have a limit x star in X. Now this implies that for any epsilon positive, there exists some number m such that if you take any number n larger than or equal to m, the distance between xn and x star is less than or equal to epsilon over 2. This is just a consequence of the fact that x star is the limit of this sequence. Now we're going to use the triangle inequality and the contraction property. So suppose that we have any number n larger than or equal to m, where we have just defined m, and consider the distance between x star and the image of x star. We're trying to prove that this distance is actually 0. Now, by the triangle inequality, it must be less than or equal to the two distances shown on the right side of this expression, and this is true for any n. Now use the fact that xn plus 1 is just the image of xn to get the expression on the right. Now use the contraction property for the first term on the right, so the distance between the images of x star and xn must be less than or equal to lambda times the distance between the points themselves. And this must be less than epsilon, because n is larger than or equal to m, so the distance between the limit x star and the terms xn, xn plus 1, and so on are all less than epsilon over 2. Lambda is less than 1, so we get the expression shown on the slide. Now this of course implies that the distance between x star and its image has to equal 0. We know that a metric cannot be negative, and it can't be positive either, because the distance between x star and its image is less than epsilon for any epsilon positive. So therefore it must be equal to 0, and x star is the fixed point of t. Now it must be a unique fixed point because we know that t, being a contraction, can have at most one fixed point. And furthermore, we've seen that x star is the limit of a sequence where each term in the sequence is the image of its predecessor, starting from any arbitrary term in the metric space. And this completes the proof of the result that we were after. If X is a complete metric space, and T is a self-map on X which satisfies the contraction property, then it has a unique fixed point, and iterating this map starting from an arbitrary point in X takes us in the limit to this fixed point. And again, if you think of X as a set of functions, and the distance as being the sup metric, then this gives us a procedure for finding the fixed point, which itself is a function, by starting from an initial guess and just iterating the map. Okay, to finish up, we'll show by example that a pseudo-contraction T may not have a fixed point, even if X is complete. And here's a very simple example where X is simply the non-negative real numbers, and T of X is X plus e to the minus X. Now you can see immediately that T of X is strictly greater than X for any non-negative X, and so therefore this has no fixed point. And furthermore, you should verify T of X is in fact a pseudo-contraction. So this example tells us that a pseudo-contraction may not have a fixed point. Now note that the set X here is complete, but it's not compact because it's not bounded. And we saw in the last segment that a subset of Euclidean space is compact if and only if it's closed and bounded. Now later in the course we'll see that if X is compact in addition to being complete, and T is a pseudo-contraction, then it does indeed have a unique fixed point, and we can approximate it with the same procedure that we use for contractions. But we'll deal with that later in the course, and I'll stop here for this segment.